So what we were looking at is a way to visualize how cos theta performs, and that is to say, for want of a better phrase, as the angle increases, the adjacent shrinks in size, which is different to sine theta, wherein as the angle increases, the opposite increases in size, and therefore for our angles 0, 30, 45, 60, and 90 degrees, we can say that if you set the hypotenuse at 2, you can recall the relationship between opposite and hypotenuse by saying the angle increases by a unit value of 1. The opposite side increases by a unit value of 1 for these increases in angle, and that's what produces this there. And that unit value of 1 is underneath a square root, or this square root value of it, so root 0, root 1, root 2, root 3, root 4. Here on the cos function, we said that as you go up through the angles, as your angle increases, for every value of 2 for your hypotenuse, you end up with root 4, root 3, root 2, root 1. So it's decreasing by a unit value of 1 under the square root sign here. So square root 1 minus or taken away from each one of these values as you move along. And that can be visualized by noticing how the adjacent is dropping in every circumstance. The adjacent is dropping through. So here you can see the adjacent has decreased. These are not to scale. But on 1, you can visualize it by seeing that at this point, it has gone from this value here, drop down to this value here, and then drop down again to this value there. If I can produce a better coloring so you can see that. So at 30, at 45, at 60, the value of the adjacent is dropping there. Considering again, just as a quick recap, that the adjacent side of our triangle is that there, and that is why it has decreased at 60 degrees to that length, which we know for 60 degrees is a length of 1 relative to a hypotenuse of 2. And it is relative, that is not to say that it is always 1 for 2, it is that it is always, the hypotenuse is always twice as big for an adjacent length of 1. Or for any adjacent length, the hypotenuse is always twice as big if the angle is 60 degrees. So we can sketch this out. So here you can see it started at 35 degrees. And then all I've done in this diagram here is I've decided to suggest to you, let's put them all on one structure. So I've gone round here. So start there, and I keep traveling all the way around until finally I reach what would otherwise be what happens when cos reaches 90, for which the angle is 0. There is no angle there. Now, you can actually notice that this first quarter here is the equivalent of this section like that. If I was to tear the circle in half, as this, for example, depicted here, so I tear the circle in half, so half the semicircle is here and the other half goes off in that pattern, you can consider that I would otherwise keep going round this circle quite considerably. I can go all the way around to 360 degrees. And so you can see between 0 and 180 degrees, I would pan out. So there, this would be this point here. This would be this point here. This would be this point, of course, that is the 0, that is 0 degrees there, but at 0 degrees in the triangle. But that is to say the value of cos 90 is 0 there. That's perhaps the better way to describe it. Because the angle is from there to here, which at that point there is 90 degrees. And then you have a circumstance wherein I'm moving round this circle. And so I would carry on that pattern as I go round 360 over and over again. I would carry on that pattern to produce this shape here. So if someone said to me, well, what's 60 degrees? In this circumstance, what is the output value of cos at 60 degrees? I'd say, okay, from this line here that I have, I'm going to draw out about 60 degrees. That triangle that I get here has an adjacent height of about, we know what that is because we've described it, it's a 1. So it would be 1 here. And so the output value of cos 60 would be 1 relative to a hypotenuse value of 2. So cos 60 is 1/2, 1/2. But what's interesting then is if I said to you, well, what about cos 100, something along those lines? Well, to do cos 100, I would do at about 90 degrees was here, so about 100 degrees, I would probably put something like that. So if I were to draw that out, I could say, well, I can draw a line to the straight there. There is my right angle triangle in these circumstances, like so. I could reflect it on the other side as well, of course. So I could suggest that you could consider it from this side. But then I would know that the circumstances are that 100 degrees is a reflection of what would be, if I do this, 80 degrees for this triangle in here. And so what I would say is wherever it was at 80 degrees, which if I use a different color we might be able to pinpoint. So about 80 degrees would be something like here. So there's our 80 degrees. If I were to go backwards and illustrate exactly what I mean to you by 80 degrees, I can probably do that. And that would be from this red line here, because that's the adjacent line. 80 degrees would probably be something like there. And so the right angle triangle would look like this. And what I'm suggesting to you is that if I was to ask what happens at 100 degrees, I could just reflect that in this image and note that they're equal to each other. It's just that at 100 degrees, you'd get a negative sign, like so. Of course, this pattern continues. If I go around in a circle 360 degrees, so 90, 180, 270, 360 degrees, I'm starting again. So the reason as to why this part of the graph over here is exactly the same as this part of the graph over here is because I've just gone round the full circle. I've gone round the full circle, so now I'm tracing out the same triangles again and again. And it can take some time to get your head around this, but at the same time, sometimes it can also feel intuitive. It depends on your background and practice. But this graph is a representation of the triangles that are mapped out in a circle-like structure wherein the adjacent length is along the y-axis. That's the adjacent length. The hypotenuse is the radius of the circle. It does not change. That is consistent. And the opposite goes along the top or bottom, with the right angle being at position like so. And again, what does cos represent? It represents the relationship between adjacent over hypotenuse. And so that is the shape of cos theta. To conclude, sine theta is a synonymous shape graph. And the reason for this one might come out to you now that we've discussed sine theta. Sine theta, the angle increases from 0 to 1 to 1.4 and so on. Now, in these circumstances, as I've shown you in this diagram, as the angle increases, we move around a circular motion like this, starting from 0, 30, 45, 60, 90, and then it will just reflect perfectly round. Hence, the sine function produces this shape as well. So it's very similar to the cos function, bar the fact that it doesn't start at this height, but it goes round, starting from 0 degrees, nice and flat here, wherein this is the adjacent side this time. The opposite side is this. The hypotenuse of the triangle would be here, and that hypotenuse stays constant. We kept it at length 2. You can keep it at any length you wish. The natural circumstances for it to be at length 1, but more than anything else, as tradition and ease for mathematics later, and also then you could do multiplication, transformations of multiplying by 2 if you want it to be greater, or 3 or 4, whatever you wish to multiply it by later. But these are the hypotenuse values which stayed constant, 2, 2, 2, 2 for cos theta, staying constant in this diagram, constant hypotenuse all the way through. It should stay the same. And for the sine theta, again, I kept it constant, 2, 2, 2, 2, 2. You could describe it as 1, because don't forget it's a ratio, it doesn't really matter. 2, 2, 2, 2, 2. And notice the opposite side grows as the angle increases, as we have discussed, and the adjacent side changes equivalent to how cos theta does so. So there's y equals sine theta and y equals cos theta. And thank you very much for getting through that one.